The modern e-learning industry frequently operates on a flawed premise. Designers build courses based on media fads, client preferences, and aesthetic intuition, rather than data. Global disruptions like the COVID-19 pandemic forced a massive transition towards synchronous remote learning, dropping millions of people into dense video conference grids. When designers treat these digital spaces like blank canvases for creative expression, they overwhelm the brain's working memory. The resulting cognitive overload severely degrades actual learning. We must treat instructional efficacy as an engineering discipline, where design choices are governed by quantitative effect sizes. And we do not have to guess what works. We have access to a central repository built from over 30 years of cognitive science meta-analyses. This matrix categorizes every major instructional intervention into specific data points. We can track the specific instructional principle, the strength of its evidence, and the moderators that dictate its use. The evidence column functions as a predictive metric. It measures the raw statistical probability that a given principle will actually improve cognitive processing. The true structural logic, however, lies in the moderators column. These are the strict boundary conditions dictating exactly when a principle will succeed or fail. Applying a scientifically validated principle outside of its specific boundary conditions neutralizes the intended benefit and increases the learner's cognitive burden. We are going to systematically map this matrix. We will isolate the high-yield principles that reduce mental friction and pinpoint the exact scenarios where their logic breaks down. Guaranteeing a functional cognitive architecture requires us to treat instructional design as a strict mathematical cost-benefit analysis. Filtering the data exclusively for interventions with a strong evidence rating isolates the non-negotiable guidelines. The multimedia principle establishes the baseline. There is a measurable cognitive advantage to combining relevant graphics with verbal explanations rather than using text alone. But this rule is constrained by the coherence principle. Using excessive, decorative graphics forces the brain to process irrelevant stimuli, which damages the encoding of the core lesson. The visual data must also adhere to the contiguity principle. This demands that printed text and related graphics be perfectly aligned in both space and time. Look at this standard format, a complex graphic on one side with its legend isolated opposite. Forcing eyes to scan back and forth consumes working memory. Resolving this friction requires detaching text labels and locking them directly onto corresponding components. The final primary structural requirement involves how the system responds to the user, the feedback principle. The empirical data reveals a sharp divide between normative feedback, simply telling a user if they are right or wrong, and explanatory feedback, which provides corrective information. In complex task training scenarios, giving a learner basic right or wrong normative feedback provides almost no measurable learning advantage. These bedrock principles provide the structural framework for digital instruction, ensuring the learner's resources are focused on the content rather than the interface. Yet every one of these bedrock rules must pass through the context filter, the moderators column. The most impactful moderator is prior knowledge. Existing expertise dictates a learner's exact visual processing requirements. This visualization places a novice beside an expert, feeding both the same graphic. For the novice, the graphic generates a massive comprehension spike. For the expert, the identical graphic offers zero advantage. Efficiency flatlines because they bypass the visual using an internal mental model. We see similar inversions with the redundancy principle, which states you should avoid adding on-screen text that simply repeats the audio narration word for word. The standard logic proves that forcing the brain to process identical text and audio simultaneously overloads working memory. However, the language proficiency moderator dictates exactly when you should ignore this rule. If the instruction involves highly complex terminology, or if the learners are non-native speakers, adding redundant text captions to paste versus learner-paced moderator yields a similar exception. Giving a user direct control to pause and scrub video playback effectively mitigates the cognitive damage of redundancy. Universal best practices are an illusion. A designer must map the demographic boundary conditions of their audience before selecting a single instructional principle. Scrolling down to the Special Applications section of the data matrix, we find emerging formats like immersive virtual reality and serious games. Look closely at the matrix here. Unlike the bedrock principles, The evidence rating for these high-tech formats explicitly reads, "Depends on design." Designers frequently operate under the flawed assumption that the immersive medium of virtual reality automatically guarantees higher learning outcomes. The hardware means nothing if the cognitive load goes unmanaged. Immersive tech fails completely if designers neglect to strip away irrelevant sounds and visual clutter. To function at all, high-tech deployments must rely on basic interventions, like pre-training the user on core concepts and segmenting the experience into manageable steps. This introduces the final metric for instructional architecture, the cost-benefit ratio. Consider a highly efficient intervention, like the personalization principle, which requires writing explanations in conversational, polite language. Applying conversational language costs absolutely nothing to implement, yet the empirical data shows it yields moderate to strong results, often generating a higher return on investment than a complex, high-budget VR simulation. As the research base expands, the discipline is moving away from relying purely on static post-test outcome measurements. We are transitioning toward real-time cognitive measurement, utilizing biometric and neuroscientific technology. Wearable biometric devices track affective reactions, heart rate, and mental fatigue while the learner engages in naturalistic settings. Eye-tracking metrics are replacing subjective user surveys. We no longer have to ask learners what they focused on. The hardware precisely isolates exactly which visual elements drive engagement. By prioritizing this empirical checklist of moderators over aesthetic intuition, we can engineer learning environments that reliably facilitate the transfer of knowledge.